Hello everybody, this lesson is about the reactions in aqueous solutions. First I will start with some small definitions and then I keep going in depth. A solution is a homogeneous mixture of two or more substances. The solute instead is the substance present in a smaller amount and the solvent is the substance present in a larger amount. A solution may be gases such as air, solid such as an alloy, or liquid like seawater. In this section we will discuss only aqueous solution in which the solute initially is a liquid or a solid and the solvent is water. Regarding the electrolyte properties, all solutes that dissolve in water fit into one or two categories: electrolytes and non-electrolytes. An electrolyte is a substance that when dissolved in water results in a solute that can conduct electricity, results in a solution that can conduct electricity. A non-electrolyte doesn't conduct electricity when dissolved in water. This figure shows an easy and straightforward method of distinguishing between electrolytes and non-electrolytes. A pair of inert electrolytes here is immersed in a beaker of water. They are electrolytes. To light the bulb, electric current must follow from one electrolyte to the other, thus completing the circuit. Pure water, here the figure number 1, pure water is a very poor conductor of electricity. However, if we add a small amount of sodium chloride, the bulb will glow as soon as the salt dissolves in the water. How you can see here in figure number 2 and finally in figure number 3. Solid sodium chloride, an ionic compound, breaks up into sodium, sodium and chloride ions when it dissolves in water. The sodium ions are attracted to the negative electrode and the chloride ions to the positive electrode. Comparing the light bulb's brightness for the same molar amounts of dissolved substances helps us distinguish between strong and weak electrolytes. A characteristic of a strong electrolyte is that the solute is assumed to be 100% dissociated into the solution. This table lists examples of strong electrolytes, weak electrolytes, and non-electrolytes. Non-electrolytes are like pure water and they aren't able to conduct electricity, while strong electrolytes are those that dissociate 100% in water and they are a strong conductor of electricity. Water is a very effective solvent for ionic compounds. Although water is an electrically neutral molecule, it has a positive region like hydrogen atoms and a negative region like oxygen atoms. Like if I want to show them like that. For this reason, it is a polar solvent. When an ionic compound such as sodium chloride dissolved in water, the three-dimensional network of ions in the solid is destroyed. The sodium and chloride ions are separated from each other. Here, for example, it shows sodium and this one it shows chloride ions. And undergo hydration. The molecules of water surround them and separated them. Each sodium ion is surrounded by water molecules, orienting their negative poles toward the cations. Similarly, each chloride ions are surrounded by water molecules with their positive poles oriented toward the anions. positive points like hydrogen oriented toward negative, but here negative points oriented towards positive sodium. I want here to briefly mention that acids and bases are also electrolytes. Some acids, including hydrochloric acid or sodium and nitric acid, are strong electrolytes. I will write here. Like acids like hydrochloric and nitric acid are strong electrolytes. These acids are assumed ionized completely in water. For example, when hydrogen chloride gas dissolves in water, I can write here hydrogen chloride gas dissolves in water, it forms hydrated hydrogen. AQ here shows aqueous. It means that they are surrounded by water molecules. And chloride, again in aqueous form. Okay, on the other hand, certain acids such as acetic acid that we have, which gives vinegar its tart flavor, don't ionize completely, and we show them like that. Acetic acid is this acid, and when they dissolve in water, they don't completely ionize, so we show them with double arrow, and the product of this solution is acetate ion and hydrogen. In comparison to hydrochloric acid, a weak acid, and this acid is not a strong conductor of electricity. Okay, and from now we will discuss three major categories of reactions that occur in aqueous solutions: precipitation reactions, acid-base reactions, and redox reactions. In this lesson, I only focus on precipitation reactions. However, from the next lessons, I will teach you the other reactions in aqueous solutions. One common type of reactions that occur in aqueous solution is the precipitation reaction, which results in the formation of an insoluble product or precipitate. A precipitate is an insoluble solid that separates from the solution. Precipitation reactions usually involve ionic compounds. For example, when an aqueous solution of lead 2 nitrate is added to an aqueous solution of potassium iodide, as you can see here, lead 2 nitrate with potassium iodide, a yellow precipitate of lead 2 iodide is formed. So this product is solid and it precipitates. Okay, here. How can we predict whether a precipitate will form when a compound is added to a solution or when two solutions are mixed? It depends on the solubility of the solute, which is defined as a maximum amount of solute that will dissolve in a given quantity of solvent at a specific temperature. All ionic compounds are strongly electrolytes, but they are not equally soluble. Here in this table, you can find a number of common ionic compounds as soluble or insoluble. Keep in mind, however, that even insoluble compounds dissolve to a certain extent. We will use this table right there in our examples. It's not necessary to memorize all of them. Just keep in in mind some of them. For example, you have to know the first column of the periodic table here that has these, metals that you can see, it's ions like here. They are called alkali metal ions, and also the ammonium ion. All the compounds of alkali metal ions and ammonia are soluble in water. The compounds containing nitrates, bicarbonates, and chlorates, halides, and sulfates, they are soluble. And we have instead those that are not in this category, they are insoluble exceptions. Insoluble compounds like carbonates, phosphates, or chromates, they are insoluble. However, here it has been shown that not all halides, but halides of silver, mercury, and lead, they are insoluble. Keep in mind some of the items. So now I'm gonna to solve a problem here. This example applies the solubility rules in the previous table, because it's asking us classify the following ionic compounds as soluble or insoluble. Although it is not necessary to memorize the solubilities of compounds, you should keep in mind the following useful rules. All ionic compounds containing alkali metal ions, the ammonium ions, and the nitrate, bicarbonate, and chlorate ions are soluble. For other compounds, we need to refer to the previous table. Let's solve it together. For the first compound, we have to refer to the previous table. As you can see, let's go back. For the silver and sulfate, as you can see, sulfate are not here in the category of the soluble compounds, and also sulfate in the category of soluble compounds, however, we have an exception which shows that the sulfates of silver ions are insoluble. So, but not all the sulfate compounds, but silver sulfates are in the category of insoluble compounds. So I have to write here insoluble. For the second compound, calcium carbonate, we can find it here. Carbonates are in the category of insoluble compounds, and also, as you can see, we don't have calcium even in this category. So all these compound is insoluble. Again, insoluble. The third compound, sodium phosphate, we can guess because sodium is in the category of alkali metal compounds, and all the compounds containing alkali metals, sodium, are in the category of soluble compounds. So when a compound starts with sodium, mostly, 90%, they are soluble. So I will write here a soluble compound. Well, okay. Now I want to talk about these parameters: molecular equation, ionic equation, and net equations. What are they? The equation describing the precipitation of lead to iodide here is called a molecular equation. This equation is a molecular equation because the formulas of the compounds are written as though all species existed as molecules or whole units. A molecular equation is useful because it identifies the reagents, that is lead 2 nitrate, for example, and potassium iodide. If we wanted to bring about this reaction in the laboratory, we would use the molecular equation. However, a molecular equation doesn't describe in detail what actually is happening in solution. As pointed out earlier, when ionic compounds dissolve in water, they point into their components, cations and ions. To be more realistic, the equation should show the dissociated ionic compounds into ions. Therefore, returning to the reaction, this reaction between potassium iodide and lead 2 nitrate, we can separate all ions and write the above equation like that. It seems like that if we dissolve these compounds in water, they would be surrounded by water molecules, and we have such a thing in aqueous media. The preceding equation is an example of an ionic equation, as it has been written here, which shows dissolved species as free ions. However, on the other hand, as you can see in ionic equation, we have the ions in the reagents that remain the same in the products. We call them spectator ions, like nitrate, potassium, which are exactly the same. Spectator ions, or ions that are not involved in the overall reaction, they can be eliminated from the equation, because spectator ions appears on both sides of an equation, and they can be eliminated from the ionic equation. So I can eliminate them from the ionic equation. Finally, we end up with the net ionic equation, which shows only the species that actually take part in the reaction. So if we eliminate the spectator ions, finally, and we rewrite this equation, we can have a net ionic equation which shows those ions that really involves in the reaction. And even here, there is another example of the barium chloride and sodium sulfate, that you can see the molecular equation here, while if we want to dissociate all these molecule compounds to their ionic compounds, and we show that if when they're dissolved in water, they break up into their ions, we have this ionic equation. And by looking to the both sides of this equation, we can find the spectator ions like the previous example. So what are the spectator ions? Sodium chloride, sodium and chloride ions that are present in both left and right sides, they are spectator ions. And I can eliminate them from these two sides like that, and by rewriting this equation I can find the net ionic equation, which shows me the real ions that participate in the reaction. As an example, write it and solve it for yourself. Next lesson I will solve for you. Predict what happens when a potassium phosphate solution is mixed with a calcium nitrate solution, and write the net ionic equation for the reaction. To predict that if this reaction leads to the precipitate, which has two, you can get an help from the previous table that we have used for our examples. Also, in this lesson, I have provided you another example which could be a little bit interesting. Which of the diagrams here accurately describes the reaction between calcium nitrate and sodium carbonate? For simplicity, only the calcium and carbonate ions are shown. Based on the definition of the reactions, I mean the precipitation reactions, or the definitions that I told you in this lesson, you can predict that the final product of this reaction has a specific form, which form is related to the final product of this reaction. Follow me. The next lesson I will talk about acid-base reaction, and also in the description of this video, I have provided some practical problems with their answers for the precipitation reaction. So you can solve different problems regarding the precipitation reaction, and also you have the answers. Good luck. See you in the next video.